So our first speaker will be Dave Farley about scaling up. Dave, stage is yours.
Thank you very much. Welcome, everybody. So I'd like to talk about scaling up today. And I think maybe it's possible that I mean something slightly different to what you have in mind, or at least something slightly additional to what you have in mind. But we'll see. What I'm really talking about is scaling up in terms of scale, capacity, efficiency, and quality. And I want to talk a little bit about all of those things. But let's get started. I think often when we think about doing things on a big scale, we tend to think about stuff like we're representing in these pictures here. And there's a problem, is because software isn't really like this. Our problem is very different to the problem of creating physical things. And I think this is important to recognize, because I think this is something that's been affected our industry for a very long time. If you think about what it is that we do, we don't have a production problem. We never have a production problem. Our product is a sequence of bytes. And however complex the systems that we are creating, we can effectively reproduce that sequence of bytes error-free for almost zero cost. The bytes that represent our systems are completely copyable. We can just clone them and reproduce them and redeploy them as many times as we like for almost free. We can recreate entire systems for free. So we don't have a production problem. That's very different to if you're making aeroplanes or cars or armchairs or even donuts. That's not what it's like when we're making physical things. And so the ideas that lead you to be able to produce cars and aeroplanes and donuts effectively and efficiently don't really apply to us. That's not our scaling problem. And that's surprising, because often we tend to organize ourselves using those sorts of ideas. It means that adopting ideas like production line thinking is wrong. This is not about trying to find cookie cutter solutions to the problems that we solve, or reproducible standardized approaches even, because that's not our problem. Those sorts of techniques are effective when you have a well-defined, clearly understood process. We don't really have that to the same degree. Software development is always an exercise in learning and discovery. And if it wasn't, why would we bother? Because I say again, we could reproduce the fruits of previous labors essentially for free. So if we're not going to do that, then there must be a reason. And that must be a reason that whatever it is that we're doing now is different in some way to what we were doing before. So it's always going to be an exercise in learning and discovery. I think what that means is that we should become world-class experts at optimizing for learning. To do that, I think, if we look to what other disciplines are world-class at learning, I think we look to places like science and engineering, perhaps, science in particular. And so we want to start thinking about working iteratively, so we can look at and reflect on our ideas and our changes. We want to gather feedback so that we can understand the nature of our changes. We want to work incrementally so that our systems are more modular and we can work on parts of them without disturbing other parts. We'd like to take a more experimental approach when we look at trying to figure out how to whether our changes are good, whether our design is good, whether it's fast enough, resilient enough, secure enough, all of those sorts of things. And we want to be empirical. We've got to gather data from the real world and inform our decision-making and our work based on real data-backed learning. Software development is also about managing complexity. And for that, we need another set of techniques to manage complexity. We need to think about the modularity of our systems. We need to divide our systems into smaller parts so that we can deal with them more independently. We need to use techniques like abstraction to be able to draw lines in our systems where we don't have to worry about the detail of what is going on behind those lines. We need to think about ideas like separation of concerns, making each part of our system is focused on achieving one specific outcome of some kind, and not merging together lots of different outcomes. And we prefer to build systems that are more loosely coupled with respect to one another. So once again, we can change them, parts of them, more independently. And this is deeply important as we start to get to build bigger and more complex systems. And we need to worry about cohesion so that each part that we are working on makes sense to some degree in isolation from other parts of the system. These ideas are just as true of the organizations that create software as they are of the software itself. Information is a kind of slippery idea. We are part of information systems too, as well as the software in which we operate. So ideas like concurrency and coupling cause problems at the organizational level just as much as they do in software. These are very closely related things, and we need to think about those as part of scaling up our ability to create bigger, more complex systems. So what do we need to do? I think first we need to start to recognize that software development is a creative discipline. It's not a cookie cutter kind of exercise. We are not stamping out new versions of systems all of the time. Each system is designed and created and, you know, the outcome of thinking and learning. Dependencies in code and in organizations are caustic, and those are the principal points that tend to slow us down and cause trouble as we start to build software on bigger scales and more complex systems. So we should start to apply more creative engineering style thinking to developing software systems so that we can start making these more evidence-based decisions. So here are a few principles that I think are important if we were to adopt a more engineering-led approach to software development than most software development is practiced on the whole, in my experience. First, we need to recognize that we should optimize for learning. We need to allow ourselves the time to discover and take missteps on our path to learning. If you have worked in an organization where you cut out the opportunities to refactor your changes or dump bad ideas, then you're probably making a mistake. You're not really optimizing for learning. We need also to optimize to manage and limit the complexity of the systems so that each piece of work that we are engaged in is within the scope of our heads, that we can understand it more clearly and work on it in isolation from changing other parts of the system as far as possible. One of the ways in which we can start to exert that kind of control is to create greater control of the variables that are involved. We should be able to run any test and get the same result every time. We should be able to deploy our software to any environment and get the same outcome every time. We should be able to make changes in one part and not another. All of these are aspects of controlling the variables at play. And we should think about this and apply it more deeply to our our day-to-day work. We'd like to make more evidence-based decisions. And to do that, my own approach, my preferred approach, is to take a consciously experimental approach to pretty much every change that I'm involved in. So at the outset, I'm going to come up with, identify what I think the change should be. That's kind of the characterization of what it is that I'm working on. I'm then going to form an idea of what I'm going to do. That's a hypothesis that I'd like to work towards. And then I'm going to design how I will recognize whether that hypothesis is met or not. in the form of a test or an evaluation or something that's going to give me feedback and gives me the opportunity to learn from that change. I think of automated tests, for example, as mini experiments that we can carry out in our code base. Similarly, things like A/B testing, where we take our products out into the hands of our users and figure out what our users like or dislike about our products, is another form of experimentation that is at the core of doing a world-class job, in my opinion. The other lesson that I think that we can learn from science that is kind of at the roots of scientific thinking, really, and engineering thinking too, is that we should never assume that we've got the correct answer. Instead, try to start out by assuming that whatever it is that you are thinking of right now is probably wrong. Give yourself the opportunity to make mistakes and learn from those mistakes. One of the superpowers of science is our ability, we learn more when our experiments go wrong than when it goes right. We can apply that kind of thinking, that kind of engineering discipline to software development too. I think one of the ways in which we can do that, another of these lessons from science, is to find ways to falsify ideas rather than to prove them. I can assert that all swans are white, and I can never, ever prove that. But as soon as I see a black swan, I know that all swans aren't white. We can organize our work to use falsification as a tool. However many tests I have, I can never prove that my software is good. But if one test fails, I know that my software is not good enough. Falsification is a tool. There's a couple of other important, valuable tools that I think that we can apply. Testability and deployability. These may not sound like tools, but bear with me. Let me try and explain what I'm talking about. Let's think for a moment about the testability of the systems that we create. Let's begin by thinking, what represents quality? What do we value in good code? So I would say, first, it has to work. It has to fulfill the task that it was created to fulfill. Then there are some technical measures that I would argue are hallmarks of good code. Good code is modular, loosely coupled, or appropriately coupled at least. Highly cohesive, good separation of concerns, and it exhibits information hiding. You'll recognize all of these from earlier when I was talking about the tools of managing complexity. So what do these things mean? How do these apply to it? What values do they add to our code? Modularity decomposes the problem into simpler pieces. Solutions, therefore, are more independent of one another and therefore more composable. We can organize them in different ways to achieve different kinds of outcomes. Solutions are often more scalable. If we've got a modular system, we can create new copies of a module that's in great demand and share the work amongst those copies. So modular code gives us more flexibility, more power to act on our code, and easier ability to change it too. Loosely coupled code reduces the risk of change in one place affecting another. It helps to isolate problems and so kind of adds to our ability to create more modular code. So this is good. It also helps us to decompose large problems into smaller, more understandable pieces. Cohesion. Cohesion is kind of the flip side of modularity. It gives us a focus. Wouldn't it be wonderful if the work that we were engaged in, the code on the page told us all that we needed to know to understand what was going on? That's what cohesive code can give to us. It tends to improve the maintainability of the code, and it goes hand in glove with ideas like modularity and loose coupling. If we want to have cohesive code and change it in one place without it affecting another, we don't get that if we are tightly coupled to some other part or our code is not very modular. It tends to increase the reuse. If we've got modular cohesive code, we can use it again in other circumstances, in other situations. Separation of concerns is slightly different to some of these other qualities in that I think it's kind of a tool in its own right that guides design decisions. At least it does in the way that I design code. It's commonly referred to as one class, one method, one class, one thing, one method, one thing. But the objective really is to simplify development. We would like to try and create code that is focused on achieving one outcome, as I said earlier on. And therefore, it's focused only on the outcome. If it needs to do something else as well, it asks another part of the code to work on that other thing. This helps us to reduce coupling and improve modularity. Again, you can see how all of these things are tied together. And again, simplifies maintenance, testing, and improves the composability of the system overall. Last in my list is information hiding. I'm lumping two very closely related ideas together here, kind of abstraction and information hiding. They're not identical, but they're close enough for the purposes of this conversation. Abstraction establishes points of stability in the design. If our design is abstract and is exhibiting information hiding, we can deal with the information in front of us without worrying the effect too much on other parts of the system. It allows us to hide the detail behind these interfaces, reducing the coupling, improving the cohesion, aiding the modularity and separation of concerns. So all of these things are reinforced. What allows us to put those attributes of quality into our code bases? Well, I would say in the absence of test-driven development specifically, I would say it's down only to the skill, experience, and integrity of an individual programmer and how much they are bothered to do this right now. If we're being lazy and we're not working too hard, even if we know what to do, we may not do these things. If we're very skillful, very experienced, and believe that we must do this to do a good job, then we may be able to achieve these kind of outcomes. So why did I mention test-driven development? Because I think it plays in this space. So let's just examine a little bit what I'm talking about. Test-driven development is commonly and probably most effectively referred to as red-green refactor. It's a simple description of a simple process. Test-driven development is about writing the test first, and it's only test-driven if we write the test first before we have any code. So we're going to write a test before we have any code. We're going to write just enough of the code, just the public interface to that code, to make the test run. Then we're going to run the test and we're going to see it fail. That's red. Now we're going to change the code just enough to make the test pass so that we get back to a stable position. That's green. And then we're going to, while we're in that stable passing state, we're going to refactor the code, changing it so it's more nicely designed, more general, more beautiful, whatever we value in the code. We're going to refactor it to be higher quality and the test if necessary, keeping them passing all of the time. That's the refactor stage. So we're going to write a test, see it fail, write some code to make it pass, modify the code to make it clean and elegant. Think for a moment, if you've never practiced test-driven development, or if you have, think for a moment what's going to be going through your head at the point at which you don't have anything yet, when you're going to write the code. Well, you're going to think, I don't want to make my life hard. Why would I want to make the test hard to write? So you're going to naturally try and make your life easy and make the test easy to write. So what makes a test like that easy to write? Well, a test like that is going to first demonstrate that the code works. Then it's going to be modular. It's going to be loosely coupled with respect to the system that it's testing. And the part of the code that it's testing is going to be loosely coupled with respect to other pieces. It's going to be cohesive, so we can test the behavior of this code that's in front of us and get an answer. It's going to have good separation of concerns, so we don't have to worry about all of the other things. The fact that this is talking to a relational database somewhere or a message queue somewhere, we can isolate it and we can separate those kinds of accidental complexity things. And it's going to exhibit information hiding, because we want to be able to write the test and write the test clearly and simply. So test-driven development encourages us to write code with these attributes of high quality. It doesn't take away from the skill, experience, and integrity of an individual programmer, but it amplifies that skill, experience, and integrity. It's hard to imagine being able to practice test-driven development where it doesn't make provide a forcing function, if you like, a fitness function at least, to encourage you to write more testable code. And if you write more testable code, you're going to get these outcomes. What this means is that you get more of these things. So test-driven development acts as something of a talent amplifier. It's no silver bullet. It's not going to automatically generate great code. But if you're a bad programmer, it will make you a little better. And if you're a great programmer, it will make you a bit greater. And there's not very much in software development that does that. There are not many things that we can say the same about. It's going to amplify our talent, whatever talent we have. But I think test-driven development does do that. Let me give you a little very simple example to demonstrate what I'm talking about. So here's a car. And this car has a petrol engine and it's got a start method. So when we start the car, we put the car into neutral, the brakes into the gears into neutral, we apply the brakes, and then we start the engine. So let's write a test for our car. Here's our test. We've got a new car. We say start the car, and that's it. We can't assert anything because there's nothing to assert. So having written the code before we wrote the test, we've now got a problem in that our code isn't testable. So let's just focus on making this code more testable. So here's a better car, and it's better in one crucial respect. We're going to change it so that instead of creating the petrol engine, we're going to pass that in as an argument. Remember, in reality, we'd be writing the test first. And so we would have written the test to allow us to pass this engine in. But here's my test, but I wanted you to see that so you could understand the context. So here's my test, should start a better car engine. So we're going to create a fake engine. What's a fake engine look like? Well, here's my example of a fake engine. We've got the start method, and it's just going to record the fact that start was called, and then we've got a method that allows us to query that. That's all it does. In reality, if we were really doing this in a project, we'd probably use a mocking library or something to automatically generate some code that did this for us. But I just wanted to make it clear what was going on. So now we're going to create a better car, and we're going to pass in the fake engine. We're going to say start. And now we're going to assert that the engine was indeed successfully started. This is now testable. So what does that mean for the design of our better car? Remember, all we've done is change this to be more testable. Let's imagine that we wanted to use this better car in some context. We can create a petrol engine just as we did before. But the car this design is more modular. We've got two modules now instead of just one module, the car, which incorporated the engine. We've now separated out the engine. That means that if we wanted to create an electric car, we could pass in an electric engine without changing the better car at all. Or if we were some kind of crazy person and we wanted a jet-powered car, we could pass in a jet engine. This code is more flexible, it's more loosely coupled, has better separation of concerns. All of these things are added just by making this code more testable. The other tool that we can use to start to inject some of these ideas into our code bases and our thinking is the deployability of our systems. One of the ideas that I talk about a lot in the context of continuous delivery is this. This is a deployment pipeline, and deployment pipelines are sometimes misunderstood too. My idea of a deployment pipeline is that it goes from commit all the way through to a releasable outcome. That means that at the end of the deployment pipeline, there's no more testing to be done. There are no sign-offs to be done, no integration tests with other components of the system. The pipeline is the definitive statement on deployability. If all of the tests pass, the release candidate that we evaluated is available for deployment into production, with no more work than pushing a button or something like that to move it into production. That's what a deployment pipeline's for. That's the definition of a deployment pipeline. So we need to take these kinds of ideas seriously. Modularity, information hiding, separation of concerns, abstraction, cohesion. These are at the roots of our profession. It doesn't matter what the nature of the systems that you build or the technology that you employ. If you write code that is more modular, has a better separation of concerns, better cohesion, and so on, it's going to be better than code that doesn't have those things. There's little to argue about that. It's going to be more flexible, more composable, easier to work on, easier to test, all of these good things. So thinking about these things, these are the principal tools that allow us to scale software development. If you have code that has those attributes, it means that teams can work more independently of one another, focusing on changes in one area of the code without worrying too much about impacting on other areas of the code. If you think about it, if you think about what's unpleasant with working with some big ball of mud monolithic system, it's because the degree to which the various parts of the system are tightly coupled together. If those code bases, however they're stored in a repository, whatever the technology, if they are modular and loosely coupled, that's not a problem anymore. It's easier to work on those kinds of systems. So these are the evils that we need to fight against in the designs and the implementation of the systems that we create, particularly as we start to think of doing this at bigger scale. So what does scaling really mean? We can scale the size, complexity of the systems that we create, certainly. We can scale the size of the organizations to create them more quickly. Actually, we can't really do that very well. That doesn't work very well, scaling up. We can, there are ways in which we can do that, but it's not a great tool. As Fred Brooks famously said in the 1970s in the wonderful and depressingly still enormously accurate book, The Mythical Man Month, you can't make a baby in a month with 9 women. There are degrees of parallelism beyond which you cannot go. There are severe limits to the amount to which you can scale a problem. And software doesn't scale very well. There's some lovely metadata research that was carried out on the impact of team size on productivity and quality. In a study of over 4,000 projects, they did a metadata analysis where they divided the groups of teams into teams of 5 and fewer people and teams of 20 and more. And then they counted, they measured how long it took each team to go from 0 lines of code to 100,000 lines of code. As you may expect, the teams of 20 people or more beat the teams of 5 people or fewer. But on average, across all of the teams, it took a team 9 months to create 100,000 lines of code. And a team of 5 people were beaten by a team of 20 people on average by only 1 week. So 1 week, so a team of 20 people is 1 week faster over a period of 9 months than a team of 5 people. So a team of 5 people is almost 4 times as productive as a team of 20 people. And then when you look at the amount of the quality of the work that they produce, the large teams, the teams of 20 people or more, created 5 times as many defects in that 100,000 lines of code. So small teams matter. If you want to scale up, you scale up by having many small, independent, small teams, not by having larger, more coordinated, larger teams. We scale up by scaling decision making. We scale decision making by making it pervasive, distributed, and continuous throughout the organizations in which we work, not by building complex hierarchies and passing decisions up the tree. That's the end of my talk. I'm about on time, I think. So thank you very much. I'm very happy to take any questions now. And while we're on the screen, if you enjoyed any of the stuff that I've talked about, would like to know more, do check out my YouTube channel. If you go to YouTube and search for Continuous Delivery, you'll find it, or there's a link down here in the bottom left-hand corner.
Thank you very much for the magnificent talk. It was really great. And please, those who listened, go to the polls channel and answer to the question there. You can rate all the presentations, and you can basically vote from 1 to 5 if you like the topic, if you like the presentation, etc. And then there is a Q&A channel, and in the Q&A channel you will find the relevant questions. So let me just search for them as well. By the way, how did you feel on the conference, Dave? So have you attended yesterday?
I couldn't attend yesterday. I was working with a client, unfortunately, so I'm hoping to attend some of the sessions today.
I see. Just let me just, I'm searching for the right tab here. Okay. So, give me 1 second. It doesn't load me. The page doesn't load.
Sure.
Do you see the questions in the question poll on the Hopin page?
No, I don't.
Okay.
I haven't got the Hopin page open. Sorry.
Yeah, that's weird. So let me just. Come up here.
So while we're waiting, I'm going to talk. You carry on. You tell me when you're ready. But in the meantime, I'm going to talk about one of the ways of thinking about scaling organizations. There's a thing called space filling network. It's a mathematical idea. So how do you define a network and kind of fill space? And there are two common types. There's kind of the directed graph, the kind of hierarchical structure. And if you think about the way that most organizations are structured, they're structured around those kinds of hierarchical organizations. You have managers, reporting lines up to managers and all that kind of stuff. And then you have distributed organizations where much more like sort of matrix management or kind of a cell-like structure where there's much looser relationships between the parts of the organization. There's a group called the Santa Fe Institute for working on nonlinear dynamics. And interestingly, this is funded by Jeff Bezos, amongst other people. But they've been doing research into the maths of these sorts of space-filling networks. And these numbers that keep cropping up over and over again. One of these 85% or 0.85, if you double the size of a organization that's structured as a directed graph, you'll increase its productivity by only 85%. It won't double because of the cost overheads of the communication problems. Similarly, if you double an organization that's hierarchically organized in that way, you only have to add 85% of the infrastructure. So you get costs of efficiency that way around. Mm-hmm. For the other kind of space-filling networks, the numbers are very different. If you double the size of those little bubbles, those independent bubbles, an organization like that, you more than double the productivity of the organization. The number that keeps cropping up for those kinds of networks is 1.15 or 115%. Amazon is organized like that. So if you double the size of Amazon, it more than doubles in productivity. It costs it more to grow. So there's some deep maths here going on. So if you want to really scale up your organization, you need to go for a more distributed organization. You need to give each of the pieces more autonomy and distribute decision making, as I said at the conclusion of my talk. It's interesting stuff.
Yes, it's a nice, interesting models that you presented. And here is, finally, I go to the questions. One question from Dave. Great talk as always. And what have you found to be the best way to introduce TDD to programmers who have never done it before?
The best way to do it is to sit alongside somebody that's familiar with it. That's the easiest way, and that's not always possible. So I think there are two things. There's kind of the desire to want to learn it. So the rationale for why it's a good idea. And I tend to talk from a point of view of engineering and the impact on design of the code, because that's what I value in it personally as a developer. But the other part are the kind of the technical skills, and the second part's the easier part, to be honest. It's harder to get people to try it and to begin than it is to actually learn the skills, I think. It takes some skill. It takes some learning to do it. The best way to learn is to practice with very simple coding exercise called coding katas. So if you Google for coding kata, K-A-T-A, it's like a repetitive exercise. Things like FizzBuzz or adding fractions or those sorts of very simple problems. And then you practice test-driven development. You adopt the discipline of not allowing yourself to write a line of code, solution code, until you've got a failing test that demands it. And if you do that, and you do that for half an hour every day for 2 weeks, just focus. You do the same exercise over and over again, but do it as a pure exercise in training. You will have a much deeper understanding of what it takes to do test-driven development, and you will learn more about that. There's a great free online service called cyber-dojo.org, where you can go and practice TDD it's got a bunch of these katas set up for you, a variety of different technologies. You pick your technology, pick the problem you want to solve, and just practice the TDD cycle. So I would head over to cyber-dojo, cyber-dojo.org, have a look at some of the katas and do one of those for half an hour every day.
This is an interesting topic, this test-driven development, and I have seen in my company in many projects it was very, very successful. In other projects it was not so that successful, but I guess it always comes down to the when to apply thing, right? There's another...
I am these days. I'm pretty test obsessed. I use test-driven development pretty much exclusively on stuff that I work on. But there are bits of the problem that are harder to test. I have a video on my YouTube channel about testing at the edges of the system. It's at the edges of the system where your system touches the real world is often the hard part, the place where you're talking to a real user or you're storing stuff in the file system. Those are the tricky parts for doing unit tests. So you abstract those in the design and you do the bulk of your testing in abstract, faking out all of those things. And then you just worry about those as kind of corner cases of the problem, I think. But I think it's pretty widely applicable. My own thing is that I hope that one day when my granddaughter learns how to write her first line of code in kindergarten, she does it in the context of test-driven development.
Let it be so. Okay, there's one more question from Renee. In my experience, most code I have seen so far is either lacking abstraction or has abstraction where there's not needed, so like over-engineering. What is your experience, and why do you think this is?
I think that's true both ways. I think the more common failure is not lacking abstraction. Most of the code that I look seems to be kind of linear, a stream of consciousness rather than an active design. We haven't tried to break out the different responsibilities or different ideas in the code. We just kind of write a sequence of steps like a recipe or something. And I think code is more than that. So that's one of the things. One of the tricks that I use is readability. And my goal in writing code is if I'm doing a really good job, then I feel like I should be able to show my code to somebody that's never seen code before but understands the problem that I'm working on, and they can at least understand what it's trying to achieve. They might not understand the context of where it's sitting with everything else, but the stuff in front of them will be readable enough. And that's one of the tricks that I use. If you have to really read the code and kind of pore over it to try and figure out what's going on, it's not abstracted enough, to my mind. If you've got a piece of code and you try and describe it, in the olden days, there used to be a way of doing OO design that was called class responsibility collaborators, CRC. Mm-hmm. Okay, so you identify a class, you say what it's responsible for, and you look for its collaborators. I think that's still a pretty good idea. It's still not a bad way of thinking about things. So if we come up with a piece of code, what's its responsibilities? How could you state in just a few words what this is doing? If you ever say this does this and that, that's poor separation of concerns. So you should be abstracting out the and part. That should be somewhere else, to my mind. And so these are rules of thumb, but they're the kinds of guidelines that I use to try and hit the sweet abstraction in my own code.
Mm-hmm. Thank you for the answer. Let's take the next one. It's from Stefan, and he asks how to break down big software projects to small teams. Do the topics microservices and domain-driven design help in this, or is there any other practices?
Yes, they do. Actually, if you're buying into microservices and you're following that in definitional terms, you're also buying into domain-driven design, because the definition of a microservice is it's aligned with a bounded context in your problem domain. So domain-driven design is important. It's an important tool to be able to do this, because that's the way of identifying areas of the problem that are more naturally decoupled from other areas of the problem. So that's important. I think Eric Evans' Domain-Driven Design book is one of the more important books that's been written in our profession during my time. It's a difficult book. Eric says that it's a difficult book. The middle part is hard going, but there's some genuine brilliance in that book and the thinking behind it, in my opinion. So yeah, domain-driven design, certainly. Microservices are trickier than many people think, and they're not where I would naturally start. I think they're where you want to end up, probably, if you want to scale your system really big. It is the most scalable approach, but the way in which it scales is that each of the microservices should be independently deployable. Yep. That too is also in the definition. And if you need to test your service with other services before you release it, means it's not independently deployable, which means that the microservices need to be appropriately abstract. And that's a difficult thing to get right at first. So certainly the experts that I know in the microservices field, and my own approach is, you start off by not building it as a microservice, but you build it as a service-oriented architecture, but you keep it together until you've riffed on it enough to be able to understand how to reduce the coupling between the pieces. You've played with it enough to start figuring out how to isolate these interfaces better. Then you can consider pulling these things out as microservices, more independent of one another. Mm-hmm.
Okay, thank you for the answer. Next question from Janos. What do you think about the concept that organizations start replicating the system or software structure?
Yeah, Conway's law. Absolutely, I think it's true. And almost impossible to duck. I worked with a client a few years ago who had built the system as one very large team, a monolithic system. They'd then read all about agile ideas and all of the funky stuff that we do. And so they decided to decompose the team into many small teams. Each team had got tired of the other teams breaking their code, so they pulled it out into a separate repo. And had continued working on these things. They drifted apart, and when I spoke to them, they hadn't even been able to compile the code together for the last 18 months. So they'd done the opposite of Conway's law. They'd had a system that was designed with one organizational structure. They changed the organizational structure so that it no longer fit the system, and that caused this problem. Mm-hmm. So absolutely, I think it's very difficult to avoid that. You can use it as a tool the other way around. You can design the organization that you want that is more aligned with the kinds of outcomes that you want technically, which is what Amazon did. So Amazon broke their organization into many small, famously called two-pizza teams, and gave those teams complete autonomy. And that allows them to get this 1.15 scaling factor of these small distributed teams because they're autonomous. So you trade off coordination and consistency for scale, which is one way of going, which is the microservices way of going, or you work in a more coordinated, more coupled way. You're going to go a little bit slower. There's probably some more constraints on how scalable you're likely to be, but you might be able to do some. You might be able to do some more. You'll be able to do more consistent work with more greater consistency. And those, to me, it seems, are the choices.
Thank you. Very interesting. Next question from Randy again. Can you say more about test-driven design development as the talent amplifier? What have your experiences been in teams that have adopted TDD in terms of team productivity, outcomes, etc.?
Yeah, so there's people haven't really done much research on TDD recently, but at the start of the century there was quite a lot of academic interest, and what the variables are kind of confusing. There's some data around quality. So there was some research that was academic research that was carried into the ways in which systems fail in production, and they found that 58% of production failures are caused by the simple mistakes that all programmers put into code, whatever the nature of the code, off by one errors, scoping problems, conditionals the wrong way around in conditional statements, those sorts of ideas that we're all familiar with. And those are essentially eliminated by a decent job of testing, automated testing. So if you practice test-driven development, you're going to eliminate about 58% of defects. There's some other data around the productivity of teams that apply these kind of approaches in a continuous delivery sense. And that says that teams that have high scores on stability and throughput, which are measures of quality and measures of efficiency, usually very closely tied to automated testing, deployment pipelines, those kinds of continuous delivery techniques. They spend 44% more time on creating new work than teams that have poor scores on those measures. So this is a more productive way of working. So it's quicker, it's more efficient, and largely because you spend less time fixing defects in production. So there isn't very clear data on TDD in isolation from other practices. But if you look at teams that practice TDD in combination with a bunch of other practices, the numbers are staggering. They are dramatically more productive, dramatically more efficient, producing significantly higher quality code as a result. So what we're seeing, I think, is that quietly we're seeing bigger organizations starting to adopt more and more of these kinds of practices, I think, over time. And I hope, it's my belief that one day we ought to get to the point where it's considered unprofessional to write production code that isn't covered by tests in the way in which I've described.
Thank you very much. Dave, thank you very much for your talk and for answering the questions. Here is something for you I have to present. This is a small mug, and this is you, by the way. This will get posted to you, so you will enjoy your coffee or tea sometime from it, hopefully.
That's correct. Thank you.
Yeah, so thank you very much once again.